I'm going to talk about Mercury, which is a new KZG-based multilinear polynomial commitment scheme, joint work with Ariel. Yeah, so let's get into it. Talk about why you should care about this, what we accomplished, and then kind of some background context. I expect people here are probably familiar with the sum check protocol. And like why we should care about this, and then kind of like the existing landscape of KZG MLPCS. You kind of have these constant size MLPCS that require linear sized FFTs, and you have linear time. So I will say time, but all of this is KZG based, so over elliptic curves. So in some sense, it's technically not linear time, but just for convenience to avoid adding that caveat every time I talk about it. What I mean by that is like a linear sized MSM. And those MLPCS are log size. So that would be like Gemini, which is what Aztec uses. And Mercury is able to kind of get the best of both worlds. It's constant size, meaning it has a constant verifier complexity, and also linear time. So yeah, the sum check protocol has, over the last few years, become extremely popular in like high performance SNARK protocols for a couple of reasons. It replaces linear or univariate polynomials, which things like Planck were used with multilinear polynomials, because we can avoid FFTs. So if you know how Planck works, you have to do basically a product of univariate polynomials and division, and that requires extending to domains. And so FFT algorithms take quasi-linear time, and sum check allows us to avoid this. Subtle point about that is that the benefit often isn't really the time, it's like the memory to do an FFT. So sum check is also useful on constrained proving environments like phones and whatnot. So if we replace our univariate polynomials in the IOP with multilinear polynomials, we need a different kind of polynomial commitment scheme. Polynomial commitment scheme is just a way to prove that you evaluated a polynomial correctly. So this makes sense. There are really nice univariate polynomial commitment schemes like KZG, but multilinear is more complicated. So that's why we care about multilinear polynomial commitment schemes. Yeah, so like I was saying before, the existing MLPCS require a trade-off. And maybe just like also to say for motivation, we care about the elliptic curve setting because they yield concretely smaller proofs and they can be efficiently checked on-chain. So that's another maybe caveat. But yeah. So the two ways you could do a multilinear polynomial commitment scheme with KZG are with a product, basically, which gives you O1 proof size, but like I said before, requires an FFT in order to compute a quotient. Or, as in Gemini, you can do a kind of, it is itself reminiscent of the sum check protocol. There are a bunch of different SNARKs that have this kind of pattern where you shrink something down by factors of 2 log time. And this allows us to do linear MSM work. It is, like I said, not technically linear, but Mercury, we can get both. Also, it's interesting to note that Mercury does like less overall prover work than existing linear time MLPCS like Gemini. We do 2n scalar multiplications instead of just 3n for Gemini. And this is with the standard KZG pairings. If you were to use an additional pairing, you could actually get it to the same asymptotically as KZG, which is pretty cool. Yeah, so just some definitions to when we talk about sum check. Multilinear function f has degree 1 in each variable. So that means that the terms of f will look like 1 and x1 times x2, and so on. There are 2 to the n terms, or 2 to the k. Multilinear extension is the unique multilinear function, like polynomial, that interpolates some values. So we usually talk about the domain like 0, 1, a Boolean hypercube, when talking about multilinear extensions. The sort of process of multilinear interpolation has a very nice structure. It uses these EQ functions, which are kind of like the Lagrange functions in univariate, and they decompose as a product like this, which will be important for how the MLPCS works, and in fact is important for how other MLPCS work as well. Yeah, so this function, if you kind of stare at it for a while, probably convince yourself that when you evaluate it with the x's being all 0 or 1 and the y's being all 0 or 1, you get 1 if the 2 inputs are the same, and 0 if they are different. And to see why, like imagine they're different at some position, then you'll have like in the first term 0 times 1 or 1 times 0, and in the second term you'll have the opposite, and so one of the factors will vanish. And so by interpolation, we mean we can write everything as like a linear combination of the values of the MLE by the EQ functions. So yeah, this is all pretty standard sum check stuff. So what is an MLPCS? It allows a prover to convince a verifier that some committed multilinear extension, when you evaluate it at any point u, gives you a value v. There are lots of different types. So if you've heard of IPA or bulletproofs, that yields essentially a multilinear polynomial commitment scheme. Basefold is explicitly multilinear polynomial commitment scheme based on Frye. Gemini, linear time KZG based, etc. Some of them have like a natural kind of MLPCS, like I said before, right? There's this way in which a lot of snarks fold things by half and like randomly combine the halves. And this is very similar to what SumCheck does. And so like if you want to do an MLPCS for bulletproofs, it turns out to be like extremely natural. Or Frye is also very natural. This is not the case for KZG. So we have this tradeoff. Mercury does sort of both things. Right, okay. So we'll talk about the 2 existing ways that people do it, because Mercury sort of combines both of them. The constant size multilinear polynomial commitment schemes work by reduction to a univariate sum check, basically. So, like I said, we have our MLE, f hat, and we can write the evaluation claim itself as a sum of products. So that is a sum check. In this case, it's written over the Boolean hypercube. But you can imagine that the EQs and the f hat are actually given as vectors. So there are other types of sum check protocols. Like in the beginning I said multilinear sum check, but sum check can be defined for univariate polynomials as well. This is like people call the Aurora sum check, where you evaluate at 0. In fact, it can be defined for polynomials over like kind of arbitrary kind of shaped hypercubes. So to get a constant size KZG MLPCS, once we write it like this, as a sum of products, we can use like an inner product protocol, or you just could interpolate the 2 vectors with polynomials, multiply them, and then do a sum check. Lots of different ways you could do this. We have a protocol in the paper that I think is interesting. It's like, compared to existing inner product protocols, it commits to like half as many values, using an interesting symmetry of, the identity. But I won't get into it here. If you look at the paper, it's there. Also, so the encoding that we use is pretty simple to describe. It's on the next slide. You take your values and sort of imagine them as a vector, and you multiply each one by a subsequent power monomial. So the Boolean hypercube, right, is bit strings. It has a sort of canonical ordering, as integers. And so if you do this, it has lots of nice properties. And in particular, when you encode the EQ function like this, it factors. This is a trick that like Halo used, and it's ubiquitous in these kinds of protocols. So that's what I mean by you can avoid committing to the EQs. Okay. So that's the constant size MLPCS. The linear time MLPCS work, like I said, kind of similarly to SumCheck. There are sort of two, I think, that we think about, Gemini and also Zeromorph. They're fairly similar. For technical reasons, Aztec uses a variant of Gemini. So again, we start with MLE and evaluation claim, and this is the encoding that I was talking about before, where you take all of your evaluations and you sort of order them according to the canonical binary hypercube ordering, and you multiply each one by a subsequent power of x. Same encoding. So we want to relate like this encoded univariate to some kind of structure for the MLE. So I write F for the univariate and F hat for the MLE. We have the same evaluation claim as before, but just written out explicitly. We define a sequence of partial evaluations of the MLE. So notice that when you partially evaluate an MLE, you get a new MLE of like a domain of half the size. So you just plug in some U's, and you have the remaining variables. Then we can define a univariate for each of these smaller MLEs. Notice the not having a hat. So this is the identity. I don't work out all the algebra in the slides, but this is sort of the Gemini identity, and I think that's the first place I saw it, but you can take the even coefficients of each univariate and the odd coefficients of each univariate. And this is the same thing as specializing the original MLE to 0 or 1. So if we take a linear combination of those, there's a slight error. I think it should say fi plus 1 of x. Well, I guess it depends how you define it maybe. But in any case, you take the linear combination of the even and the odd coefficients, and it's the same thing as specializing the first variable. So this allows us to relate the univariates, like fi to fi plus 1, in the same way that we related the MLEs by evaluating in the first variable. So this is like a folding operation. And the reason this is useful is because we have a univariate or a univariate PCS. So if we had a commitment to fi, we could evaluate fi even from evaluations of fi. And so we can relate evaluations of each of the folded univariates in this way. In particular, we can link FIR and FI negative R with FI plus 1 R squared. So this is essentially what Gemini does. From here, it's not too hard to work out the rest of the protocol. You have these like subsequent folds, and you want to check them all at different points. And there's, subtleties, but proceeds naturally. So this is the idea of Mercury. Gemini, we're always folding by a factor of 2. And you see here, I say like FIR and FI negative R. You imagine that the prover sends evaluations for these to the verifier. So Gemini folds by a factor of 2. It folds log times, and it sends 2 values each time. So the transcript is log sized. If we could fold by a factor larger than 2, we could use fewer rounds, right? If we could fold by a factor of 3, we would send 3 values each time. If we folded by a factor of square root n, we'd send like square root n values in one time, maybe. But like, so concretely, if you were to do this, you might use flonk, which is a way to decompose a polynomial into sort of pieces in like this sort of FFT decomposition. But you'd send 1 value per each piece. So if you fold by a factor of k, you'd send k values. So if we wanted super like constant folding factors, you would increase the proof size. Like I said, if you folded by a factor of square root n, the proof size would then become square root n. So in building a constant size MLPCS, we don't want this. The main trick, I think, that Mercury does is we can fold by a factor of k and only send O of 1 information. Like prover only sends a single, or O of 1 commitments to polynomials, instead of setting k values. And we can prove, like construct this proof in linear time. If we had that primitive, which we do, then we could fold once by a factor of square root n, and then use the slow, like FFT-based MLPCS to check that the folded thing like relates properly. So even though, you know, we're doing something that's n log n, you're applying it to a vector of length square root n, and it doesn't affect the overall running time. It's interesting to note that like we pick square root n because it's optimal for our use case, but you could fold by a factor as small as log n and still get a linear time prover overall. Yeah, exactly. So, yeah, and yeah, but in our case, you know, it's square root n, so it makes sense. Okay, so the way that we do this is not so complicated. I think this slide might be missing like one line, so sorry if that's confusing. But we, instead of sending k evaluations, so we need to back up a little bit. In the Gemini case, we send two evaluations at r and negative r, which you can think of as a coset of the degree 2 roots of unity, like 1 and negative 1. This generalizes in Flonk to a coset of the k roots of unity. So you'd send like an evaluation at r, an evaluation at r times omega, r times omega squared, up through k. If you think like some simple like algebra, sending a bunch of evaluations is the same as sending like a polynomial reduced mod a polynomial whose roots are the points evaluations that you care about. And the polynomial whose roots are the k, or like the k root of unity coset of r, is x to the k minus r to the k. It's like if you plug in omega times r into this equation, it'll vanish. So instead of sending evaluations, we can send the reduction mod this polynomial. And then from that, you can evaluate it to the points that you care about, because the modulus vanishes. And so this is what we do. We have f, we decompose it, and this is the piece I'm missing. These f sub i's are like the interleaved k order coefficients of f. In the case of k equals 2, f0 would be like the even coefficients, and f1 would be the odd coefficients. And so if you reduce mod x to the k minus r to the k, you replace all the x to the k's with r's to the k's, and you get a polynomial of degree k minus 1 as g. So if we could check this congruence of polynomials, then we would be able to check that we sort of folded f by evaluating each piece at an element of the k coset determined by r. That might sound more complicated than it actually is. And we can compute all of this in like, well, yeah. So another like technical point is in Flonk, you need to use r to be a kth residue. This is not the case for Mercury. You can be any value in the field. And so, yeah, that's just the identity I was describing before. If you multiply r with power of kth root of unity. So implicitly here you have this like a quotient, which is multiplying the vanishing polynomial, and you also have g. And in order for the overall protocol to be linear time, we have to show that you can compute both of these quantities in linear time. And it turns out that you can. The intuition is if you take each of the interleaved chunks, each of the f sub i's, and you want to construct a quotient, it's sufficient to consider it as a polynomial of degree n over k, and compute the quotient as you normally would, and then interleave the quotients. So it's not so bad. That would take n over k time, and then times k is n time. So this is the overall protocol sketch of Mercury. I've found in the past trying to describe it in words confuses people more than just writing it down first. So hopefully this is clearer than it would have been. We have the same public input as before. We have like our commitment to F, our evaluation point U, and our evaluated result V. And we let B be square root n. This is written sort of parametrically. Like I said, you could let B be log n, or any value from log n up to n over log n. So that's our FFT decomposition I was talking about. You split F into B pieces, and each one will be of degree n over B. This is the like Gemini-style univariate encoding of our MLE. Then you take the evaluation point and split it in half, U prime and U prime prime, which are like the first log B coefficients and the second n over log B, or log of n over B coefficients. If B is square root n, U prime is just the first half and U prime prime is the second half. So we commit to the result of the first folding. So a linear combination of the pieces by the EQ functions. Then pick a random challenge and commit to the folding of F by that random challenge. So we have two sort of, you could think of it kind of like a commutativity diagram or something. You like go in one way where we fold by the EQs, and then you go in the other way where we fold by alpha. And we want to check that those two things agree. So if we take the folded polynomial G and we do an inner product with the EQ functions, this should be the same as if we take H and evaluate it at alpha. And this is because if you were to, so suppose we evaluate H at alpha, we get each Fi to be at alpha times EQ. And if you look at the definition of F, folding by alpha replaces the x to the b by alpha. And then doing an inner product takes the inner product of those values. So it should be the same. This lets us check that H was correctly constructed. And it runs in time like square root n log square root n or something. Then once we check H is correctly constructed, we can do another inner product with the rest of the coefficients. This also runs in square root n log square root n time. So these final two steps are both sublinear. And the only linear step is actually the folding. Concretely, committing to Q and then committing to an evaluation of F in order to like reduce all these polynomial identities to a single KZG check are the most expensive parts of the protocol. And that's where we get the factor of 2n, like in the overall work the prover has to do. Everything else is basically like square root sized. So it's all very cheap. Yeah. Let's see. I think that's basically it. It's worth mentioning there's another work that came out like a few days after Mercury called Samaritan, which is like essentially the same construction presented a little differently. And there is a way in which you can sort of think about this like a bivariate sum check. It's maybe not exactly the same, but I think it's an interesting thing to think about and kind of expand upon. But yeah, I think if you're using a multilinear polynomial commitment scheme that's based on KZG, like Gemini or Zeromorph, you should probably consider or just switch to Mercury or Samaritan because the prover is simpler, the verifier is simpler, it's constant size, less randomness. Yeah, so that's it. Any questions?
Thank you very much, Liam. Do we have any questions? Okay, I'll start with one. You mentioned SumCheck has some nice memory efficiency properties. Are they preserved here with the commitment scheme?
I think so. So the SumCheck like memory efficiency properties that I was talking about come from not needing to compute a quotient. I'm not sure. I'd have to think about it more. I would assume probably, but I think there's usually a trade-off, especially in like the very low memory SumCheck protocols of like increasing time, so you like would reconstruct the witness. If you did that, I think this would definitely be compatible with that.
Thanks.
Unless you reconstruct the witness, SumCheck is not memory.
Yeah. Yeah. Any other questions? No, in which case, thank you very much, Liam.